Welcome to Module 11 of our AI for Beginners video course. In this module, we will explore the fundamentals of natural language processing, or NLP, and learn how to teach machines to read. Following our look at image processing in the previous video, we are now shifting our focus to text. We will walk through 5 parts, from loading our data to training and reflecting on a text classification model. In this first part, we are loading and exploring our text data. To get started, we will use a classic dataset that comes built right into the scikit-learn library. We are using the 20 Newsgroups dataset, which contains thousands of real posts from the early 1990s. We will narrow this down to 2 distinct categories, similar to the simple iris dataset we used in Module 9. To load the data, we use the _fetch_20 Newsgroups function, specifying the categories we want to analyze. The raw text is stored in _news.data, while _news.target holds the classification labels. Here is a first look at the data. Each entry is real, human-written text. It is important to remember that this data can vary slightly depending on your version of scikit-learn, so consider these examples as illustrative. Next, we check the class balance. By using _np bin count on our target labels, we can confirm the number of posts in each category, which in this case is roughly balanced. In part 2, we move from words to numbers. This is the crucial step that allows any machine learning model to process and learn from natural language. Why do we need a translation step? Because models require numerical inputs, but language consists of variable length strings of characters. We must convert these into fixed length lists of numbers. The bag of words approach is a simple but useful method. We count how many times each word appears and ignore grammar or word order. For topic classification, this is often sufficient. For example, if we have 2 sentences, we can represent each as a vector based on the unique words in our vocabulary. This transformation turns different sentences into matching length lists of numbers. We implement this using _CountVectorizer. By setting _max_features to 2000, we ensure that every document is converted into a vector with exactly 2000 columns, regardless of its length. We can further upgrade this process by removing stop words, common filler words that carry little meaning, and using TF-IDF to weight words based on their relative importance across the entire dataset. Ultimately, this works because we are applying statistical pattern matching to word counts. The model doesn't understand the language. It simply identifies correlations between specific word frequencies and categories. In the next part, we will discuss preparing this data for the actual training process and highlight a common trap to watch out for. Now that we have our numerical data, it is time to prepare for training. We must split our dataset into training and testing sets, ensuring we do so before any vectorization to maintain the integrity of our results. A common mistake is fitting the vectorizer on the entire dataset. This creates "data leakage," where information from the test set influences the training process. Instead, fit the vectorizer only on the training portion, then use that same object to transform the test set. Here is the correct approach. Use _fit_transform on your training data to learn the vocabulary, and then use _transform on the test data. This ensures your model never learns indirectly from data it will eventually be tested on. With our data pre-processed correctly, we move into the 4th part of our module, training and evaluating our model. We will follow the standard pattern of fitting, predicting, and scoring, now applied to real text. For our algorithm, we choose Multinomial Naive Bayes. It is the classic starting point for bag of words text classification, because it is fast to train and works exceptionally well with word count features. Training is straightforward. We call the familiar _.fit method on our vectorized training data and the corresponding labels. It is the same process we have used since the earlier modules of this course. Once trained, we make predictions on the unseen test set using _.predict. The output provides category labels which we can map back to readable names, just as we did with the iris dataset. To measure performance, we use the accuracy_score. For distinct topics like science news versus sports, this approach typically achieves high accuracy, often well into the 90s. Before relying on a single score, it is best practice to spot check a few predictions. Comparing our model's output to the actual labels provides a quick, human-readable sanity check of our results. We can get an even deeper understanding using a confusion matrix. This table shows us exactly how the model performed, distinguishing between correct classifications and the specific types of errors it made. Remember that a single accuracy number can hide nuances. A confusion matrix reveals if the model struggles with a particular category, showing us exactly where and in which direction the model's predictions are failing. Finally, we reach the 5th part of our module, predicting on entirely new text and reflecting on the limitations of the bag of words method. To test the model on a brand new sentence, we simply pass it through the existing _transform step. This maps the new text into the same numerical format the model learned during its initial training. The model identifies strong correlations between specific keywords and categories, effectively performing statistical matching. It does not understand the meaning, but it excels at detecting the patterns associated with specific topics. However, Bag of Words ignores word order, meaning it can miss nuance, sarcasm, or negation. While it is a powerful tool for basic classification, more advanced models can account for context, which we will explore in the next module. Let's review the complete pipeline we've built. As you can see, in just about a dozen lines of code, we can load a dataset, prepare it, train a model, and evaluate its performance. To recap, our process involves 6 clear steps: loading clean text, splitting our data, vectorizing, training with fit, honest evaluation on held-out data, and finally, using the model to predict new, unseen text. You can experiment further by swapping in a different algorithm, like logistic regression, trying a different vectorizer, such as TF-IDF, for potentially better results, or adding more categories to challenge the model's accuracy. Let's bust some common myths. First, grammar isn't required for classification. Word presence is often enough. Second, more features don't always mean better results. And third, training data limits your model's real-world performance. Now, let's test your knowledge. Please pause the video to consider these 4 questions regarding Bag of Words limitations, vectorization best practices, and ways to improve the pipeline. Here are the answers. Bag of Words discards word order, leading to potential confusion. Fitting only on training data prevents leakage. Finally, negation is a major limitation, and performance can be refined by tweaking vectorizers or algorithms. Here is a quick reference guide for the key vocabulary from this module, including concepts like Bag of Words, TF-IDF, and data leakage, which are essential for your toolkit as you continue learning NLP. The key takeaways are clear. Computers need numbers to process text. Vectorization is the engine for this. Data integrity is vital to prevent leakage. And while simple, Bag of Words is a great starting point. Up next in Module 12, we will look at large language models. You have learned how to represent text as counts, but now we'll see what happens when models start reading in order and context. Congratulations! You have officially taught a machine to read. We hope this module has built a strong foundation for your journey into AI. We look forward to seeing you in our next session.